Okay, welcome guys to our third video on the 9 big ideas for college chemistry in our review sessions. So this is big idea 3. It mostly encompasses intermolecular forces and properties of compounds. We'll talk about a lot of different things. We'll get into kinetic molecular theory and small amount of spectroscopy, just some simple definitions really. But let's go ahead and get started. So we'll start over here on the left with individual types of solids. They're listed over here. We've got covalent, metallic, ionic, and of course, covalent network. For our covalent compounds, the main IMFs are going to be dictated really by their polarity. So you have, oh my goodness, this is going to be interesting. I'm having trouble typing already, or writing. So this is going to be nonpolar. Nonpolar molecules are going to only have London dispersion forces. And if you remember, London dispersion forces, which we'll talk about in a little bit, are going to be based on the number of electrons present. So the greater the number of electrons present, the more they're going to have these temporary dipoles and be affected by one another. Others are going to be polar molecules. Polar molecules can have dipole moments, or they could also have intermolecular forces of hydrogen bonding. Yeah, and these will be the things that bring together those molecules to form the solid, or there will be some attraction in liquid phase, but we'll assume there's not very much in the gas. I guess we can keep going down. Let's go across. So covalent molecules, nonpolar hydrogen bonding, and dip forces between those covalent molecules if they're in fact polar and don't contain hydrogen bonding. One of the things about these properties that are seen in the lab is this stuff is tested every year. Okay. So they're going to ask you questions about the behavior of these things in a lab based on what we have done in the lab. So you're going to have to go back and think about what we've done in the lab in terms of, boiling point, viscosity, vapor pressure, how things are attracted, not attracted to each other, high melting points, low melting points, and so forth. So having a good understanding of intermolecular forces is going to make a big difference. So if we go over here, we've got properties you would see in the lab. And this right here is for covalent molecules, so molecular compounds that are in a solid state. So they have a really low melting points. So these are going to have to be really cold to be solids. They're also going to have a low boiling point. Many of these are going to be liquids or gases at room temperature. They have low viscosity, and they do have a high vapor pressure, generally speaking. Not all of them, but many of them have high vapor pressure. So they change to a liquid, from a liquid to a gas very easily. If they're nonpolar, they're going to be soluble in nonpolar solvents. And if they're polar, they're going to be soluble in polar solvents. Like dissolves like is not really an answer for why this happens, but will help you remember what's going on. They're not conductive in the solid, melted, or dissolved states. They don't conduct electricity. And generally, as solids, they are brittle and kind of powdery. Some examples of those are like carbon dioxide, NO3, nitrogen trioxide, hydrogen sulfide gas, and hydrocyanic acid. Not all of these are nonpolar. The CO2 is nonpolar, but the others have a bit of polarity and, will form a little different. With your molecular solids, you're going to have molecules at a whole molecule at each of the lattice points. So if it were water, as in the picture, you'd have a water molecule at each one of those corners forming that solid. Okay, so for metallics are going to have various melting point and boiling points. Generally speaking, they're pretty high, kind of in the mid-range between ionic and covalent. Some of the metals can be higher than some of the ionics, but generally speaking, they're going to go in this order. So yeah, kind of a middle to high melting point, boiling point. They are lustrous, malleable, and ductile. You need to know what those things are. Luster just means it's pretty, it's shiny. Malleable and ductile have to do with being pounded into shape or drawn in a wire. They're generally insoluble, are metals, and they're non-electrolytes, but in a solid form, they do conduct electricity. So they are conductive in their solid state, and that's why they're used in wires. Some examples are iron, of course, gold, copper, often used in wiring, as is aluminum, lead, whatever. Metals from the middle of the periodic table. Okay. And kind of what they're seeing, what they're showing here, but they should probably draw it better, is that each of these are those, and they could have different charges. I'm just writing plus because it's easy. Excuse me, but there are these metallic cations in this sea of valence electrons in here. So they're not really showing the electrons, but they're networks of those cations held together by the metallic bonding, or that mesh of electrons in there. There are better models to describe this, but they're not tested on the AP exam. So the band model of molecular orbital theory is certainly better at describing what happens with these metals, but this is certainly sufficient for what we're doing. So next on the list is ionic. Excuse me. Ionic compounds are going to be between metals and nonmetals. They have pretty high melting point and boiling points, 800,000 degrees Celsius or so. They have low vapor pressure. They're not changing to a gas. They are non-conductive, but when they are molten, or they're dissolved in water, they are electrolytes. Yeah. So when those ions are free to move, they can conduct electricity pretty well, ion to ion. They're brittle and they do form kind of shiny crystals for the most part. Some examples, there's lots of them, are magnesium oxide, let's say lithium chloride, your favorite, sodium chloride, and so forth. Could also have, instead of having those individual ions at lattice points, you could have polyatomic ions, say like ammonium. Oh, let me get rid of that. I don't need that. Oh, there you go. Ammonium nitrate. So you could have like polyatomic ions at each of those ionic solid points or lattice points. And then the last one here are covalent networks. Covalent networks are going to have covalent bonds between all of the individual atoms. They have extremely high melting points and boiling points. They have really low vapor pressure. They're not changing to a gas at all, in fact. They're insoluble in all solvents. And some examples of them are graphite, some silica compounds. They are conductive in their solid state, especially graphite, great conductor of electricity. A diamond is, however, not a great conductor of electricity. Graphite does it because it has mobile sheets, and inside those sheets, there are electrons that can transfer between them. More of that band model description, but you don't need to know that. You just know graphite conducting is enough. Some examples of this would be like SiO2. So silicon and oxygen compounds can form covalent network solids, but you'll most often see it with carbon-containing compounds, or perhaps germanium, something in the same group as carbon. You could have different allotropes of this. So you could have diamond and graphite are two different allotropes, ways that you see carbon in its structure. You could add buckyballs to that list, nanotubes, whatever, graphene if you like. But those are different allotropes of that same carbon-containing elements, or covalent network solids containing carbon. So if I move over here, go into intermolecular forces, these intermolecular forces actually occur between the actual molecules. So this is one molecule to another molecule. So if I have, hydrofluoric acid or HF, there would be an attraction, a hydrogen bond, in fact, to another hydrogen fluoride or hydrofluoric acid molecule. That intermolecular force is this intermolecular force is the thing between them. It's not the thing inside the molecule. That's a covalent bond, polar covalent bond. But this would be the attraction between those two. The three different ones that we're most concerned with, or that we're going to talk about, are going to be LDF. LDFs are going to be interactions between mostly nonpolar molecules. In truth, all compounds have LDFs. All substances have LDFs based on the number of their electrons. And what can happen is the number of electrons can move to one side or another, causing temporary, I guess I can spell, temporary dipoles. And so the molecules will attract to each other very weakly. They'll attract and then they'll repel. Then they'll attract and then they let go, and so forth. The more electrons, the more polarizability, or the more polarizable the substance is. And it will have more IMFs as a result of that. So that polarizable electrons is, if you had an atom and had several electrons, you might see that there's a time when the electrons are on one side and they might actually attract to another atom or molecule that has electrons on the opposite side. So there would be a temporary attraction between those two atoms. But just as soon as they do that, the electrons go back to where they normally were and there's no attraction, or perhaps there's repulsion or whatever. But the more electrons that are present, the greater the probability of having them on one side or the other. Now, dipole-dipole interactions are going to be between polar molecules, and they're not, that's not how you spell polar. They're between polar molecules, and these polar molecules, this is as a permanent dipole, will have stronger generally attractions than the LDFs. Now, that's not true. If something has a ton of polarizable electrons like I2, then that's not true. It might be stronger than dipole-dipole. And look for those kinds of questions on your AP test where it says, why is Cl2 or why does Cl2 have a higher boiling point than, say, HCl, even though HCl has a dipole moment? And the reason would be because the LDFs are very strong in the Cl2 because it has so many electrons. Anyway, so you'll typically see this kind of show up. So HCl is a great example. That is a permanent dipole between the hydrogen and the chlorine, as there's a difference in electronegativity. So there'd be some dip-dip attractions between them. Remember that hydrogen bonding only has to be, or is only when hydrogen is bonded to an F, O, or N, and then there will be an attraction to the other molecule. So these would be pairs of F, O, and N containing elements with that on one side of the molecule, and then a positive dipole with the hydrogen that's bonded to that FO or N. You have to have both of them. So, and this would be, yeah, so it's bonded, that hydrogen that's in that compound. So if I have, go back to my HF, if I have HF, it would be the attraction, if this is the molecule here, that's a single bond, the attraction of the fluorine for hydrogen on another molecule. It could even be HCl. Now, generally speaking, we talk about hydrogen bonding in terms of it bonding with another one that is also, let's say it's a water molecule, right? Something that is FO or N bonded to something that has hydrogen bonded to an FO or N as well. When matter goes, okay, so that's all the stuff about IMFs there. But when you go through phase changes, you're going from solid to liquid to gas. The things that you are breaking are these intermolecular forces. So this attraction right here is what you are breaking to cause a phase change, to go from the liquid to the gaseous state or from the solid to the liquid state. And so that's what we're going to kind of talk about down here. So, or at least the states of matter. So from solid to liquid to gas, solids are going to have really regular arrangements. You know, solids are going to have this kind of fixed in structure arrangement. So you're going to see solids drawn in kind of cubic forms or whatever. It might not be a cube, could be anything. Liquids will be more irregular. They are going to take pretty much the same amount of space that a solid does. Now, it can vary. Solids generally are thought of as being more dense than liquids, but there are exceptions, ice being one of them, solid water being one of them. But as they become gases, they're having fewer and fewer attractions between them. And so they spread out significantly. So yeah, gases and liquids are going to be irregular in shape. They'll take the shape of their container. Solids and liquids are compressed, and while gases are not. So gases can be compressed. Solids and liquids generally cannot. Now, if you have a solid that's compressed, it's probably the fact that the solid has gas in between the molecules. Like styrofoam is a solid, but it has quite a bit of gas that's actually packed in there as well. Solids have the greatest IMFs due to the close proximity when gases experience kind of the weakest. So the greatest IMFs are going to be in the solid form, not in the liquid or the gaseous form. So if I go across, kind of going backwards over here a little bit, what I'm looking at here is what happens between the gas molecules. This is showing the speed of the molecules as a function of temperature. So as I increase temperature, what's happening is, now the lines I'm drawing are kind of right in the middle of these. They're representing the average temperature of this. So as I increase the temperature, more of the molecules are going to have a certain velocity and moving around faster. And the same is true if you move them around faster, you can increase their temperature, their average kinetic energy. But not all, they're still going to have molecules that have a small amount of energy and some that have a high amount of energy, but the average of all of them is actually going to be higher. Anyway, so what you need to know is that as, oh, that's interesting. Look at that, just drew that for me. So as T is increased, the kinetic energy is also going to increase. You know what? I could draw arrows. Let's do that because I like arrows. So as my temperature is going up, my kinetic energy is also going to go up. And that's what they're demonstrating here. Doesn't mean that all of the molecules are going to have that happen to them, but the average of them is going to have that happen as well. So that leads to the kinetic molecular theory, KMT. It says that gases are made up of small particles that really have negligible volume. They have constant motion and have minimal interactions, especially when that volume is really large. But gases are not really going to have, we treat them ideally so they don't have any contact between them or attraction between them, but that's not always the case. There's sometimes, especially when you're close to a phase change, there'll actually be some attraction or repulsion between them. Gas behavior is dependent on pressure, volume, and temperature. Temperature of a gas is directly proportional to its Kelvin temperature. So if you know the Kelvin temperature, it is, and it goes up or down, that is the exact same thing is going to be happening to the molecules and their velocities. Most ideal increased temperature is actually going to decrease pressure. This is quantified by our formula, our ideal gas law, PV equals nRT. A container with multiple gases has a Dalton's law of partial pressures dictates that it has a sum. So the total pressure is going to be the sum of each of the partial pressures of those gases. And that formula can be used to solve for, you know, a gas that's missing, or perhaps the water vapor pressure that's missing, or if they give you the water vapor pressure, you would make sure that you add it in there. So remember that the sum of the gases gives you your total pressure. The pressure of the gas and a mixture of them, if you know the partial pressure of the initial gas, and it'll be times the mole, this is mole fraction of the gas. You could take that partial pressure initial and it multiply by the, that shouldn't say initial, that should say total pressure. Sorry. That should say total pressure. Total pressure times the mole fraction of the gas will actually give you the partial pressure of the individual gas that you're looking at. Yeah, there we go. So the partial pressure of the gas in a mixture, if you multiply by its fraction, which makes sense, times the total, you'll get the individual one. And we use that in calculating mole. So to calculate mole fraction, you have the moles of one divided by the moles of all of them added together, depending on how many of them there were. And so that's what this X value represents, is that mole fraction. So kind of bouncing around, moving around a little bit here. Let's see, let's go over here to solution solvent. We can come over here and do this. Spectroscopy, and there were a couple questions, I think, of this in the first homework assignment, but that's all right. Spectroscopy, electrons are going to absorb and emit sort of measured amounts of energy, and it depends on kind of where they are as to how you're going to determine what they're doing or how to observe them. Microwaves are generally used for molecular rotation. For determining molecular vibration, infrared spectroscopy is actually used. And then the one that we're most familiar with is that we used in our colorimeters and our spectrophotometers in the classroom is visible spectroscopy, or UV. So ultraviolet and visible spectroscopy is kind of the same. What you're looking for there is the energy levels, or the change in energy levels between those. And so electrons will jump to a higher energy level, and as they go back down, they give off a certain amount of energy. We were able to use Beer's law to calculate, you know, based on absorbance, what our concentrations were for different substances, because it's a linear function. Pretty easy to do, actually. So last thing to discuss here, solutions are going to be mixtures of solvent and solute. Usually they're going to be aqueous solutions. They don't have to be. You could have nonpolar solutions and say benzene or something, or hexane, but often we'll be just talking about aqueous solutions. To calculate the molarity of those things, or their concentration, it's the moles of solute divided by liters of solution. You're familiar with this. You could also do solubility in grams per milliliter, or grams per some sort of set volume, could be liters for their solubility. Usually solubility is done in terms, if you do calculating solubility, say in a KSP problem, it would be in moles per liter. But if you were just determining solubility, say from graphic stuff, usually it's in grams of the solute per 100 grams of the solution, or solvent. Oh, stop. If you're drawing a solution, make sure that you show your ions and particles and the water molecules. We've done this a lot this year, but if you've got a K plus ion, you can draw it however you want to. If you want a little key, you can do that. If you're going to draw water molecules, I would draw them as like the ears and stuff, you know, like a Mickey Mouse. But make sure you draw the right part of the water molecule surrounding that individual atom or ion. Be careful with that. You will have to draw something on your AP test somewhere, or at a minimum, recognize where those are in the multiple choice. So this last thing, oh, lost my time there. One of the other things about solutions is remember that solutions can be saturated. They could also be unsaturated. And in fact, if they are heated up, dissolved, and then cooled back, some solutions can actually be super, not all, but some can actually form supersaturated solutions. So yeah, and so over here we've got kind of a graph. This is very familiar. We've looked at it several times, but this is showing you solubility in grams of different solvent or solutes for 100 grams of water. Notice that the majority of them go up. So solids tend to increase solubility with temperature increase. So if T goes up, solids will increase their solubility. For gases, it is the opposite. Now, this graph is not gases, but gases will decrease solubility with temperature increases. So as T goes up, gases will go down in solubility. As temperature goes up, solids will actually increase their solubility. So you need, I guess that's pretty much everything I want to discuss with you guys. But you could be given a graph like that and determine the solubility at different temperature. Very simple, very easy to do. Okay, so that wraps up 3, at least the basics for 3. There's quite a bit to actual IMFs. Made it kind of short here, but you're going to have a ton of questions over this to try and review this topic. It is one of the most difficult topics for students to grasp, not necessarily AP students, but certainly advanced and on-level students have a lot of difficulty understanding intermolecular forces. Okay, so I will see you guys in video 4 for Big Idea 4. And that's it. Okay.